Okay, so our new topic is equilibrium of rigid bodies. Now, let's begin with the generic three-dimensional rigid bodies. In fact, when we are talking about a rigid body, we have said that it's non-deformable. So it preserves its shape under the external loads. Now we may have forces and moments acting on the rigid body. In fact, remember that for a particle, so the particle is an thing, object which doesn't have a geometry. It just has a mass. We have said that some of the forces acting on the particle has to be zero for it to be in equilibrium, in static equilibrium. Now we have an additional condition in three-dimensional space. Certainly, we have the moments acting on the object, and in fact, therefore, some of the moments has to be equal to zero. These moments includes the moments generated by the external forces and moments acting on the object. So these are the two equilibrium conditions for an object to be in under static conditions. Of course, we need to design things and we need to develop some tools for the people. So we want to analyze a problem. Therefore, first thing that we have to do is to draw the free body diagram. So what's a free body diagram? In case of a free body diagram, we draw the object that we want to investigate or analyze in a schematic manner. Then we put all the external loads on the object. For example, here we have an aircraft. Certainly it has a mass. Therefore, there exists a weight acting on it. Now, it is already landed, and certainly there will be some reaction forces. First of all, we have two reaction forces coming from the tires on the wings, and we have one reaction force coming from the front wheel of the aircraft. And we don't have any other external forces or moments, or in other words, external loads in general. So this is our free body diagram, and this basically helps us in understanding the problem, and it helps us in choosing the methodology that we are going to use for solving the problem. Certainly, we have different types of joints. These objects are connected to somewhere or in contact with some places. We have different types of connections. In fact, we have some reaction forces or reactions in general, not only the forces, but also the moments, reactions coming from these supports. For example, we have cables. So as you remember that the cable only carries load along its direction. And in fact, it will pull, and cable will carry only load along its direction. What else? We have a weightless link. That's also possible. Again, it only carries load along its direction. It can be tensile, as you see on the left side. So this is tensile because we have, action equal to reaction. Therefore, there will be a force in this direction on the link, and as a result, the force coming from the link is in this direction if it is tensile. If it is compressive, then it is in this direction. So what else? We have a roller. Again, the roller will apply a force tangent to the surface that the object is sliding on. Therefore, it will only repel the object, because when you pull it, you can easily detach it. Certainly, when there is a force coming from the object like this, there will be a reaction force in the opposite direction. As a result, we have such a force coming from the roller. What else? We have a rocker. Again, it is the same. So it will behave, rocker will behave like the roller. Again, there will be a reaction force which pushes the object. Again, it is tangent to the surface. Sorry, not tangent, perpendicular to the surface. Okay, what else? So we may have smooth contacting surface, as we see here, for example. Again, it has to be perpendicular to the point of contact. In this case, the reaction force, support reaction, has to be like this. We may have a slider, okay, slot. Then certainly this type of support will not allow the motion of this object in this direction. Therefore, we will have force either like this or like this. We may have pin connected collar. So this object can easily rotate like this, but cannot move perpendicular to the collar. As a result, we will have reaction forces in the directions in which or at which the motion is restricted. So when we look at the overall supports, we see that there exists a force whenever there is a restriction of, or there is a restriction of the motion. Certainly, this beam cannot move like this. As a result, there will be a force in the opposite direction. In case of a link, again, if you want to move this object in this direction, there will be a reaction force in this direction. Or if you want to move this object in this direction, this link will pull it back. So there will be a force in this direction. So this is how the supports work. Of course, there are other types of supports. So we may have smooth pin or hinge. As you see, in this case, this type of support will not allow the motion in this direction and in this direction. Therefore, we will have forces in either direction. Certainly, it can easily rotate around this joint or this support, and there will not be any moment just because of it, because it can easily rotate. Okay, we have a fixed connected member fixed connected to a collar. Okay, so certainly in this case, as you see, the object can easily move in this direction, but cannot move perpendicular to the collar. This is not possible. And in fact, it cannot rotate around this joint. Now, prohibited motion will generate a force. Generally, it is in the direction opposite to the motion or tendency of the motion. And since it cannot rotate, there will be a reaction moment, as you see here. Now, we may have fixed support. That's another type of support we generally face with. In this case, as you see, this object cannot move in this direction. This will result a force like this, and it cannot move in the vertical direction. As a result, we will have vertical component of the force, and indeed it cannot rotate because it's fixed to the wall. So all of these motions are prohibited, restricted. As a result, we have a moment, reaction moment, coming from the support. Now the direction of these moments and forces can be arbitrarily chosen if it is not known beforehand. Certainly, if you find a negative value, this means that the direction you choose is not correct. It has to be in the opposite direction. Okay. Now, there are some fundamental things which are critical. Let's have a look at them. First of all, before solving the problem, we have to draw the free body diagram. This will help us in understanding the solution of the problem. This is one thing that we have to do at the beginning of the before begin to solve the problem. Now, second thing is we need to know a support. If a support prevents a motion in one direction, translational motion. So basically, this is a translation, and if there is a support which will avoid the motion towards the left-hand side, certainly there will be a reaction force coming from this support to this object. Therefore, we can easily identify whether there exists a force, reaction force or not, just by looking at the support. Because there cannot be a translational motion. For example, this cannot go up, then this means that my hand is applying a force downwards on the object. Second thing is, if the rotation is prevented, for example, I want to rotate it, this object, and my hand is preventing it, avoiding it. Therefore, my hand is applying a moment in order to avoid the rotation of the object. This basically means that there is a moment coming from the support to the object. We will see it much more clearly when we are going to, when we begin to solve the problems. Okay. Sometimes we use over-constrained designs because generally we want our designs to function even though there exists a problem. And as a result, we put some more constraints. In other words, we put some more supports. In this case, we have, because generally we don't know the support reactions, okay, we need to calculate them in order to make the design. And in this case, the system is over-constrained. Therefore, we call such a system statically indeterminate. So this is one important thing. For example, here we have a beam. Of course, this beam is fixed to the wall, and there are two rollers at point B and C. That's okay. Let's look at the free body diagram of this beam. Now we have AX and AY because the motion is restricted here, right? In X and Y directions, certainly. And of course, the object cannot rotate around point A. As a result, we have a support reaction coming from the point A. So we have two support reactions, forces, and moment as a support reaction at point A, whereas at point B, this object can easily, I mean, if you just isolate the system and just focus on the point B, you can easily see that the object can easily move in the horizontal direction, either through the left or through right hand side, but cannot move downwards. As a result, there will be a support reaction coming from the ground or whatever it is at point B. It is the same for point C. If you isolate the object or the part of the object there, you can easily say that it will not be able to move downwards at C. As a result, we have some normal force component coming from the joint or coming from the support at that location. So now we will continue to solve some problems.